Okay, so last time I was just doing some simple order of magnitude things about binaries, and I will say a couple of things that I forgot to say last time about that. And then I will move on to discuss how to estimate the amplitude of the gravitational wave background that one relevant for PTAs, but it's a more general than that. So I'll talk about supermassive black holes and how one goes about estimating the amplitude one might expect and how it compares with the measured answer and so on. The problem sets that Gabby and Jimmy put out, they are related to this. Gabby will, her project is to in detail go through this estimate, much more detail that I'll be able to do, and you'll do it by your, you'll actually do it yourselves. And in the case of Jimmy, it's about the question of how the black holes get into the centers of galaxies and eventually form binaries and so on, the processes. So that I'm not going to cover in the lectures, and but the problems you will work these through and kind of understand the timescales for dynamical friction and these kind of things. Okay, so binaries. So just let me repeat a few of the things that I said, just so that I can say what I forgot last time. So just remember this simple relation between velocity and frequency, or if you want V over C, which I was trying to show you that most of these things you can once you take out the dimensions, the dimensionless relevant thing is V over C. And so just was discussing the various powers of V over C, say for the power radiated by gravitational waves. And in all the formulas, there's always these 1/3 and thirds, and they're all coming from here. So binding energy, 1/2 mu v squared, and you can, mu being the reduced mass, which is equal to the symmetric mass ratio times the total mass. And so replacing this, you will see that you get proportional to eta. There's the total mass. This is this here, and so this I already said, but or no over c squared here. It's just yeah, to the 2/3. And so here again, you can take this eta. So the mass, there is a total 5/3 of the total mass, and you can split this eta in such a way that you can convert both this and that into the chirp mass. Okay, so which is eta to the 3/5 times the total mass. So this is also the binding energy can also be written as the chirp mass. You can take this out, and this would be the chirp mass, and here. And I also said that the power emitted in gravitational waves was, okay, the numbers doesn't matter too much, but, and this was V over C to the power 10, okay, and this nice constant C to the 5th divided by G. And again, you can take, so this V over C to the 5th and the 1/3, and one of the etas converts this M total into M chirp. So this would be proportional also just to, if you plug this, you replace by this so that you expose the frequency and the mass. The masses would also combine into the chirp mass. Anyway. And so I had also defined some gravitational wave timescale, and I did it by just taking the binding energy and dividing it by the power emitted in gravitational waves, you could decide, I mean, the binding energy and the frequency are just, one is the power of the other. So you can decide instead of, you could have defined the gravitational wave timescale by thinking about the variation timescale for the frequency instead of the energy. So you could do some sort of F over F dot or period over P dot. You would always get the same, except for some factors of 3/2, 2/3 from. So all I'm saying is that the energy is proportional to F to the 2/3. So if I do d log E dt, or I do d log F dt, I get the same. I mean, the time scale is the same. I would get a 2/3 in this case. So you can define it however you want, but the typical time scale is given by this. And this one is proportional to V over C to the power 10. This one is proportional to V over C to the power square. So this, in terms of V over C, this is V over C to the power 8 downstairs, okay? Again, because both the energy and this can, if you think about their scaling with the mass, is the chirp mass that is entering in this ratio. It's also the chirp mass that is entering. And so this time scale, if I drop all the constants, okay. Okay, so, and finally, I'm repeating all this because I didn't talk about the chirp or the frequency evolution at all. And I just thought that somebody needed to say that. So, so again, this F over F dot or P over P dot, they will all be proportional to 1 over this T gravitational wave timescale with a coefficient. Well, one of them will be positive, the other one will be negative. There will be a 2/3 compared to this definition, but it's always the same. Perhaps one last thing to mention, or two things to mention would be, if I think of P dot over P, this is the change of the period, the relative change of the period. If I ask the question, how much the period changes in one period, I would end up computing this, right? This is the relative change of the period times the time. This would be the change of the period in one period. So P dot is an interesting thing to compute. And this one is dimensionless, okay? dp dt is a dimensionless thing. And this one is proportional to V over C to the power 5, okay? And again, there's an eta in here. So if you think of it, if you translate this into mass and frequency, it will also be the chirp mass and the frequency. Okay, another way of thinking about this P dot, you could say, what is the relationship between the time scale of evolution due to gravitational radiation and the period? You could say, let me do the ratio of P divided by the gravitational wave time scale of evolution. Is this evolving rapidly compared to the period or not? So again, this is P over P dot. So this would be P divided by P over P dot. I'm just doing very simple stuff, huh? P dot, okay? So again, the relative time scale of the period compared to gravitational waves is just this P dot, which normally it's, if the thing is not very near merger, this is a very long time. It's V over C, or T gravitational waves is much longer than the period. It takes many orbits for the thing to evolve, right? So this is V over C to the fifth, so it's a small number, okay? So when we were comparing, when we were saying, oh, the luminosity here is a huge luminosity, and at the end of the day, unless because of this V over C to the power 10, in a realistic system, it's going to be significantly smaller than this, except when you go very close to the merger. But even then, you will plug 1/2 here, and still to the power 10 it would be a relatively small number. But in general, the luminosity will be small compared to that if the system is non-relativistic. On the one, in part because the energy is not of order 1 of the mass that is being radiated, but it's down by v squared, and also it's radiated over a longer time scale. That TGW is much longer than the period. Okay, so that's. I mean, this is nothing different than the PGW formula because I'm getting at everything from the same place. But if you want to think about it, you can think of it like this. So typically, you are much less efficient. You can define some sort of efficiency, like how much of the energy of the total mc square of the system is being radiated away. It will end up being a small number down by V over C squared if you do the total energy. And if you're thinking about the power, it will be also significantly smaller than this Planck luminosity because it's also being radiated on a very much longer time scale than the period. Okay, this is just very simple. Finally, so you can integrate, if you want, this equation f dot over f equals, well, if I want, do I want to put the, I don't, so this formula, let me just do like that, because of its 2/3 that I define. And so this thing is then proportional to f, if I'm counting now. So I can integrate this in time to figure out the evolution of the frequency as a function of time and seeing the typical chirp that we know and love. And so to do that, I just plug in the formula for the gravitational wave timescale, which is gone, or I never wrote it, but in terms of the frequency over there, yeah? And so this is proportional then to frequency to the 8/3. And so you can integrate this, so, exercise, integrate this, and find frequency proportional to 1 or t minus t of the merger to the minus 3/8. So the 3/8 is this one. Okay, the integral is this f, and then you're done. Okay, so and then the other thing that I will leave you as an exercise to do. Yesterday, I think Teja drew some sensitivity curve of LIGO, say, for example, and said the amplitude, this is frequency, and this was the noise, and frequency. And then this was like the signal, looked like some sort of power law, meaning the amplitude of the gravitational wave emission as a function of frequency. How do you derive the slope of that, power law? So we are talking about now h as a function of frequency. Okay. How does it depend on frequency, the amplitude? We know, on the one hand, I had given you that the amplitude in the time, like the signal in the time domain, this was proportional to g mu the distance, and then the velocity v over c squared. And this v over c squared is this f, in terms of frequency, f to the 2/3, right? So part of this, part of that frequency, the h of f, how it depends on frequency, is coming from this v over c. But that's not all there is to it, because for that plot, we are talking about the strain as a function of frequency. So the Fourier transform of this, so it's h of f, say integral dt e to the I 2 pi f t h of t. So because of the chirp, the signal is not staying at a given frequency forever, right? So there's only a limited amount of time over which the signal is staying at any particular frequency. And so the amplitude there not only is just given by the amplitude of this h, which is this, but also by the fact that this guy is oscillating with a changing frequency, and only during a small amount of this dt integral will you get a contribution, okay? And so how do you estimate, or how do you get the time scale over which you are kind of in phase and you're accumulating the integral, okay? That's all about, if the frequency was a constant, let's say for a very, in the case of PTAs, maybe supermassive black holes, their frequency evolution is very small, very low, slow compared to the time of observation. In that case, you would be doing this Fourier transform over a finite period of time in which this thing has a fixed frequency, and so then you will only get a non-zero value of this h of f when the frequencies match, and the integral will just give you the length of the time of observation, okay? But in the case of LIGO, that's not the regime you're at. The frequency changes very fast compared to your time scale of observation. So what sets the time scale is basically how fast the frequency is evolving. So what sets the time scale is the time derivative of the frequency. It's because there is a time derivative of the frequency that you only get a contribution for a small amount of time. You can do this integral by the stationary phase approximation, for example, but okay, roughly the answer exercise, do that and see that the time scale that would enter here is 1 over the square root of this would be the time that would make this. When you do the stationary phase approximation, you will get the amplitude and also a time, which will be given by this, okay? And then the combination of the time dependence of the frequency dependence of f dot and this f to the 2/3 is what set that slope. So I leave you as an exercise to calculate that slope or show that it's f to the -7.6, okay? Which is the, any questions about this? No? Okay, so these were just things that I forgot to or didn't have time to say yesterday. So now for a change of topics, or for, let's start discussing something else. So I want to discuss what one might expect if one wants to estimate the background of gravitational waves for a collection of sources that are emitting gravitational waves all throughout the universe in the context, for example, of this pulsar timing array signal, okay? So the idea then is that you have a collection of sources as I just said there, so let's say we're somewhere here, there's a region of the universe, and let's say the expanding universe, there's a collection of sources, and we are somewhere here, okay? The energy of all of these sources, so the gravitational waves emitted by all of these sources, fills the universe, fills this box, okay, and creates an energy density that Bruce already talked about of gravitational waves in this box in the universe, okay? The universe is expanding, but it's all of this energy emitted by all these binaries that create this background. I just want to estimate the energy in this background, okay? So each of these sources, you know, if you wanted, so you can go about it in two ways, and we will, maybe later I will do the other way, but one way, which is the one that I will do later also, is to take, say, here I am ignoring all the polarizations, all of this stuff. This is just for order of magnitude purposes, okay? So strain of the gravitational wave, each of these sources, and you are somewhere here, a distance d away from the source. We just said that the amplitude is proportional to the chirp mass, to the 5/3. And so I'm trying to compute the energy in these sources at a specific frequency, okay? So one option is to start taking all of these sources, and each of them generates a strain given by this, and try to add, you know, add that up. That's one way of doing it, and I will do that. And so my assumption will be that there's some certain number density of these sources, okay? That's the, and if you want, there's a certain number density of these sources. The way I will think about it will be something like this. So let's take the context of the pulsar timing array. So there's these supermassive black hole binaries that are merging, and you know, the black holes live in the centers of galaxies. The galaxies merge. Eventually, these black holes sink into the center. They form a binary. Eventually, the binary somehow gets sufficiently tied to emit a lot of gravitational waves, and eventually they merge. So they put out a certain amount of energy, each of them, and then you have the black hole left, okay? And this black hole is somewhere here in the, you know, in the local universe. All these galaxies have a black hole that perhaps are the results, or in their history, they merge with somebody else, okay? So there is, if you want, a number density of these black holes in the local universe, which are the remnants of these mergers. And somewhere in the history of the universe, they merge. Let's say each of them merged once, just to keep it simple. But they could have merged many times, or none, or not at all, okay? But so I have this number density of these remnants, and I know that for each of these remnants, at some point in the history of the universe, they merged once or twice or half the time, I don't know, some rate of, or some probability that they merged, okay? So on the basis of that, I want to try to estimate the energy density in the gravitational wave background, okay? Or the energy density in some logarithmic frequency range, right? So then the easiest way to go about it is to think about these individual sources, and because they merged once, they've put out some amount of energy, which is this binding energy that I erased, right? So if I know the frequency, the binding energy is proportional to f to the 2/3. If I know the gravitational wave frequency that I am looking at, they put out in that frequency band a certain amount of energy. And this energy is here in this box somewhere, right? So the total energy density is given by the number density of these black holes and the amount of energy that each of them put out, right? And I need to take into consideration that the universe is expanding, so I need to do that. And I also need to take into account the fact that the radiation is redshifting as the universe expands. So okay? But so if I know the number density of these black holes, I can do this computation, I can do this estimate. So remember that remember then that the amount of energy in a certain logarithmic frequency range is proportional. So as I said there's these 2/3 that I'm now carrying around for not particularly good reason, but okay. So this is the binding energy or the amount of energy per logarithmic frequency range in the orbit that's what's getting radiated away. Okay, and so any question about this? No. So okay, so what is, if I wanted to write a formula for the amount of gravitational wave energy in a given frequency range, then let me be a little bit careful about the expansion of the universe. So first, there is the part about the actual space, getting bigger, let's say, the expansion of the universe. So I will work just in comoving coordinates. So in comoving coordinates, you know, the location of objects in the expanding universe remains the same, but the physical distances are just scaled by the scale factors. So like the physical distance will be some a of t times x, where the x is the comoving coordinate. So I will just talk about a certain size of in comoving coordinates. So the fact that the universe in these coordinates, the size of the box in x coordinates is fixed. Okay, so if you if these sources, they are all there, the number density in comoving coordinates, dn comoving, the volume is constant because I'm computing everything in these x coordinates that are taken out the expansion of the universe, and there's always the same, I don't know, 4 sources there, but the universe is expanding, but I'm talking about the number of sources in a given comoving volume. So and so I'm trying to understand the density of the energy density in that comoving volume. Okay, so the formula looks something like this. So even though I've taken out the expansion of the universe for the purpose of the I'm not describing this in physical coordinates. So the number density in comoving coordinates of the sources is fixed. It's still the case that if the gravitational waves are emitted at a given redshift, their frequency gets redshifted with the expansion of the universe, right? So if I observe the gravitational waves at a given frequency in the PTA, they were emitted, if they were emitted at high redshift, they were emitted at a different frequency, okay? So this is the number density of these sources in comoving coordinates, okay? I need to take each of these is emitting this amount of energy at the time of emission, but it's getting redshifted by a factor of 1 plus z. And so that's the formula that I need to compute. And perhaps one thing interesting that happens is the following then. So as I said, the gravitational wave, observed gravitational wave frequency is different than the emitted frequency. So let's say that I'm thinking about something that was emitted at a redshift of z, then the gravitational wave frequency at the time of emission was higher than the one at the time of observation, okay, because it got redshifted away by the factor 1 plus z, okay? So in other words, is this, yeah, sorry, I wanted this way also. So, so if I now come to this formula, what I need to do is compute the amount of energy that was emitted by this binary of a given chirp mass, for example, at the emitted frequency, and I need then to redshift that energy by a factor of 1 plus z, okay? So I need to plug in here the amount of energy emitted. So I need to go to that formula and plug in the frequency of the gravitational waves at the time of emission, okay? So this formula is proportional to f gravitational waves to the 2/3. So it will be if I want to now express the answer in terms of the gravitational wave frequency today that I observed today, which is the relevant thing for comparing with the experiment, I want to replace this gravitational wave frequency at the time of emission by some expression in terms of the observed gravitational wave frequency. So I plug that in, and this then becomes proportional to 1 plus z to the 2/3, okay? So this redshift of the energy of the gravitational waves, 2/3 of it are canceled when I do this. So this integral, so this has a 1 plus z to the 2/3, this has a 1 plus z to the 1/3. So in total, even if I don't know exactly at what redshift the merger happened, the dependence on the redshift will be 1 plus z to the 1/3. We are now talking about some astrophysical merger of these supermassive black holes that happens between redshift 1 or something like that and today. So z is somewhere between redshift 1 and 0, some place there. I may not know exactly what it is. All I wanted to point out is that the dependence of this 1 plus z, so I don't know when in the redshift, I know, let's say, the black holes as they are today, but I don't know, even if they are the mergers of some progenitors, I don't know when this merger happens, but it happened in the late universe when all of these big galaxies exist and they're merging. And so somewhere 1 plus z to the z that I don't know, but to the power of 1/3, okay? So that's not a very big dependence. So the fact that I don't know exactly, if I'm trying to do this estimate of the energy density in gravitational waves, the fact that I don't know exactly when the black holes merged is not going to be a big deal in terms of uncertainty in the answer, because z of 0 to the 1/3, 1 plus z to the 1, that's a 1, but 2 to the 1/3 is also not so different from 1, okay? There will be other uncertainties that dwarf this, okay? So good. So a simple then estimate, if you follow this logic of the gravitational wave background, looks something like this. You can say that rho gravitational waves, or d rho gravitational wave d log f, is something like this. So let me take out the current number density of these sources, and outside of the integral, dz, dn, dz, 1 over n naught, and then this 1 plus z to the minus 1/3, okay? So that's this part of the integral. And then what I get is the binding energy, this d log f, which is these 2/3 of E, which is, let me say, is the mass of the black hole times some efficiency factor. I'm just defining this efficiency factor by d log E or dE d log F 1 over mc squared, okay? Okay, this is just the definition to get some, and this is the thing that is proportional to V over C. This is just V over C squared, okay? Because I've taken out the total mass. There's an eta if you want. Okay, so this is, I don't know exactly when things merged, but for all practical purposes, this is not a big uncertainty because it's just the average of over the probability of when something merged of 1 plus z to the 1/3, which, or minus 1/3, which is very close to 1 in any case. I mean, we're not talking, tomorrow I will talk more about sources that are at higher redshift, but including inflation or something like that. But for these purposes of astrophysical sources, and especially in this case, they will be nearby. So this is not a big deal. And so this part here is just the rho of the black holes. Okay, so the energy or the mass density of the black hole remnants today. Okay, this is some sort of efficiency factor that tells you how much energy of their total rest mass, how much they put out. Okay, and so that's what it is. So the gravitational wave background, we need to know what's this efficiency. We need to get some sense for this efficiency. We need to get some estimate for the mass density of black holes around us. If we had these two things, we can plug it in here and get the energy density in black holes, okay? Or in the gravitational waves produced by the mergers of these black holes. Is it clear or not? Yeah.
Factor, that ratio is the dx over the
Is dE d log f. It's just the total, the binding energy of the binary between two frequencies. So that's the energy that is being put out, and I divide it by mc squared just to know, I don't know, to call it some efficiency, right? And so to be able also to look out for the mass density in black holes today. So this now gives me a relationship between the background of gravitational wave, the energy in the background of the gravitational waves, and if you want, the energy or the mass density in the black holes around us. So now if I can estimate this using some other observations, and I have a sense, so remember that this V over C, I already erased it, but this is just, so V cubed was just Gm pi f, right? So if I know the mass, if I know the mass of these black holes, I can estimate V over C, and I know this efficiency, okay? And if I can count them or know how many black holes there are in the local universe, I know the mass density of black holes, okay? And this is nothing other. I have some source that emits gravitational waves. It only, of the total rest mass, a small fraction of it is being radiated in gravitational waves. This epsilon would be a small number. And so the energy density in the background is the density of these sources times the energy that they put out. There's nothing more to it. There is only this issue of the redshift, but it's a very minimal issue. That's I talked a little bit about this to just say that you might think that without knowing when these sources, when was the emission and so on, I wouldn't know. It's true if I'm talking about a truly cosmological phase transition, I have no idea. But if I'm talking about the mergers of galaxies, or even if I'm doing some background for LISA from white dwarf binaries of white dwarfs, I mean, this is all in some sort of redshift 0 to 1 kind of business. And so, okay, I will not know this number perfectly, but it's not the end of the world, okay? Any other questions about this? Yeah.
Can you just assume that there won't be black hole rays, like that the density?
So okay, so let's say, we see black holes around us. Now the question is, how did they come about, right? Did these black holes, they are there, they have a certain mass. Did this 10 to the 9 solar mass black hole in the center of this galaxy, did this form just by accreting matter, in which case no merger, no background? Or did a substantial fraction of the mass that was formed, that is formed, or whatever, the mass of this black hole came from mergers, from smaller ones, okay? That's a good question, I don't know. And I think now we know the answer to this. A significant fraction of the growth of the masses of those black holes came through mergers, because if not, you would never produce the gravitational wave background as large as the one as PTA has seen, okay? Now this is not, to the extent we think that this background is, has been observed and is there, is real, and its origin is this one, okay? So that's part of the, so this is part of the estimate. If we now go out and count the number of black holes around us and their masses, we estimate this, and then we are kind of done, and we plug it in, we get this, and we compare with the observations and where it stands. And I think the clear conclusion is that there's a lot of mergers, because if not, you wouldn't get such a big background, okay? Any other question? So to do this, to finally plug in some numbers and get the size of this background, we need a couple of things. We need the masses of these black holes in order to estimate this efficiency. And we also need to count them somehow, how many black holes there are around us, okay? So, okay, so let me mention two ways to count the black holes around us. I mean, the obvious way to count the black holes around, the most direct, is to actually try to count the black holes around us. Just at least, what I'm talking about is the black holes that today reside in the centers of galaxies, okay? So I can go out there, I know how many galaxies there are, I kind of guesstimate what's the mass of a black hole in a given galaxy, I multiply, I get some number, okay? I'll discuss that in a second. There's another argument, which is called the Sultan argument, which goes something like this. In addition to, in addition to merging, these black holes accreted matter, okay? When they accrete matter, they shine, okay? And so we see these black holes in the form of quasars at high redshift shining light. And so perhaps by looking at those quasars, I can try to guesstimate how much mass there is in these black holes. And it actually is not so, uncertain, or people have done this for a very long time, and they kind of have some answer, which I think is reasonable. And it goes in the following way. So how do these faraway quasars, they shine? They shine powered by what? By the energy from the accretion of material into those black holes. So the same process that is growing their mass is also providing the energy for them to shine, right? So in some sense, then there is the connection between the total light that they are producing, which is given by the accretion, and the total mass they get into, because that's the mass that is falling and producing the light. So if I can go out there and count how many, so there's some sort of formula that says that the total luminosity of these quasars is going to be proportional, and people define some sort of efficiency parameter, radiative efficiency, to the accretion of matter. So here is the m dot of accretion, blah, blah, blah. Okay, so the luminosity, the total luminosity is powered by accretion. That's the belief that the quasar light is coming from accretion. And let's say you have so this means that you have to ask the question when M is falling into the black hole, how much energy you are getting out in the form of radiation. A typical estimate is to think that you have a disk of material and there is a last stable circular orbit, so you brought the material from very far away to this last stable circular orbit, and that's the binding energy that is coming out in the form of radiation. And so that gives you an estimate for this efficiency, which is around 0.1 in this case. Depends on whether the black hole is spinning or not spinning and so on. So that's more or less a theoretical argument of trying to build a model with a disk around a black hole and so on. There's also, you can try to do it directly. You can go look at a specific quasar and try to estimate the luminosity of that quasar and properties of the disk and so on, and try to get this on a case-by-case basis, trying to see. And this is a number that, let's say, I will take for this estimate, and is the reasonable number that people many times use. Okay, so the argument goes like this. So this is the accreted mass. This part goes out in the form of radiation. The other part falls into the black hole. So the M dot of the black hole is 1 minus this efficiency times this accreted matter, okay? M accretion, C squared. And so if you, and on the other side, this accreted matter is the luminosity divided by this radiative efficiency. So you can take that M dot in the black hole is basically this 1 minus this efficiency divided by this efficiency times the luminosity, okay, proportional to this. So now, if I go out there and I look at all the quasars, count the quasars, look at their luminosity, integrate that luminosity over time, and multiply by this factor, the integral over time of this is just the growth of the mass of all the black holes. So if I count all of the quasars that I can see, and I integrate over time all the luminosity that they are producing, I will get the total amount of mass in black holes today, which is what I need to put here. I don't really need to know very much. This argument will not tell me how massive they got, but they will tell me in total, given that all of this energy was radiated out and it's just basically related to the mass that was falling into the black hole, it will tell me how much mass ended up in black holes in total, okay? So that path is called the Sultan argument, and so you end up with, yeah.
There shouldn't be a C squared end up.
Oh, because I didn't put it here, I either put it on both sides or I don't put it in any side, yes. So here I'm thinking the amount of energy that's being radiated, and so because I'm going to equate to the luminosity, then I am having the C square there, okay? But then I dropped it from here because I'm being sloppy, so I will do like this, okay? Yeah. Any other question? No? So that's one way of doing it. Okay, you get some. So when you do that, you get an estimate for the energy density or mass density in black holes, which is around 5 times 10 to the 5 solar masses per megaparsec cube, okay? That's what you get if you put this radiative efficiency of order 0.1. So this is a very old argument. This comes from the early days of observations of quasars and so on. So people had a sense of how many black holes, the total mass of black holes that were around, okay? So if I combine this with some mass of these typical black holes that I see around, and the ones that produce most of the gravitational wave background would be around 10 to the 9 solar masses, I can then estimate this efficiency, and I have the gravitational wave background energy. A more detailed estimate will come from actually trying to count the black holes that we see around it. So I will discuss this now. The other thing that I wanted to say is that if you look at this formula, the amount of energy in a given, how this depends on frequency. If I look at different frequencies, how much energy is in the gravitational wave background in a given frequency range, other frequency range, is all coming from this V over C squared, right? So the slope of this background is fixed by how much binding energy there is in the orbit in the different frequency bands, right? So there is not much freedom. If I've observed the background at a given frequency and its origin is this, at least for the average amount of energy, which is what I'm computing here, the amount of energy in different frequencies is kind of fixed by this formula. So there's no two ways around it. So the slope, at least of the amplitude of the gravitational waves, of the slope of the spectrum of the amplitude of gravitational waves that the PTAs have seen, should match if this binding energy in the binaries are going into gravitational radiation, the slope is just given by this. So if you see some frequency band, the next frequency band, it needs to be this and that or the other, just given by this. You don't have very much freedom, provided all of the energy in the binding energy of the orbit has gone into gravitational radiation, which is all I'm doing here, okay? If there's some other process to which some of this binding energy is going, then the gravitational wave background would be smaller than this in that frequency range, okay? And a little bit of that might be, you will do in this exercise. It's not crazy to suspect that part of this binding energy of the orbit might be going somewhere else. And the reason, especially when we're talking about large separations of the binary or low frequencies. And perhaps related to the fact that in order to make this binary become so close to, so you have, the idea is you have these two galaxies, they merge, they have the two black holes in the center. The black holes needs to go very close to each other, form a binary, and also the binary needs to be very tight so that it's sufficiently relativistic that it emits a lot of energy in gravitational wave and it merges. So there's some astrophysical process that is making the binary tighter, because as we were estimating the first lecture, this separation is a very small fraction of a parsec in order for them to be emitting at the, or something like that, on the PTA frequency. And so something is making the binary tighter. This is a very small separation for galactic, the two black holes started and separated by a big distance, right? The typical size of galaxies. They went into the center. So something is doing something, right, to bring them together. And so it's extracting energy and angular momentum from this binary. So at some point, that thing is more important than gravitational radiation, because gravitational radiation, we said, was such a big V over C power that, sometimes it's very important, but later it is kind of doesn't do anything, right? And we need this other process in order to bring the thing together close. So it's possible that in some frequency band, some of the binding energy of these binaries is not going to gravitational waves, but it's going to this other process, whatever, that is needed for them to become so close. And so in that case, the spectrum here will not be given just by this, because a part of this energy will be missing from this. You will see some lower amount of energy, And maybe using that, you can learn about what are the processes that bring together these black holes, okay? But if it's not because of that, especially once gravitational, you go to high frequency enough that gravitational waves take over, then the energy in the amount of energy in the different bands is fixed by this, okay? And there's no freedom. Okay. So let's be a little bit more. This is a little bit, a little bit more of astrophysical phenomenology to try to understand the black holes around us. Okay, and then from there we would be able to get a better sense about what mass we need to put in here to get the efficiency and so on. So, so as you know, hopefully you know that in the centers of galaxies, there are supermassive black holes, okay? These supermassive black holes, not only are they there in the centers of galaxies, but they play a big role in the history of the galaxies and why the galaxies look the way they look and how much stars they were able to form. Many of these processes are understood only at some level, okay? But another thing that is very interesting is that the mass of these black holes seems to correlate with the properties of the galaxy. So a zeroth order thing to keep in mind is that if you look at a galaxy, maybe it's an elliptical galaxy, or if it's a spiral galaxy, there is some sort of bulge of stars in the center. There's some certain mass of stars in the center there, either in the elliptical galaxy, the whole galaxy, or in this core of or the bulge of the galaxy of the spiral galaxy. There is, wherever you can see a black hole, or basically you find a black hole in those galaxies whose mass is basically 1% of the mass of the stars of this bunch. Why that is the case, I don't think we know, but that's a fact, and more or less an observational fact. So so there are various scaling relations that associate the mass of the black hole. Turns out the masses of the black holes in galaxies are related then with the properties of the galaxies. One scaling relation is that one that I told you, but another one that is the one that people use or that use a lot is the so-called M sigma relation. So you look at the velocity dispersion of the stars in the galaxy, okay, in the center of the galaxy, and you also, if you can, measure the black hole in the mass of the black hole in the center. And if you were to plot in a log-log plot of the mass of the black hole and the velocity dispersion, you see some sort of scaling law, some power law relation in which the mass of the black hole is more or less proportional to sigma to the 5th power, okay, more or less. There's some scatter around this relation, but galaxies seem to follow that. Again, for reasons that maybe we don't understand completely, but that's how the universe around us looks. And so we also don't know, so we may not know very well if this was also true at high redshift, and not when is the detailed properties of this relation evolving with time? Is this, does this extend to very high velocity dispersions or not? Or what, is there a maximum or what have you? This is not, there's like 100 or 200 of these black holes. It's not so easy to get the mass of the black hole. So in order to get the mass of the black hole, you need to be able to follow things orbiting around it or something like that, close to it, when the gravity of the black hole dominates over the gravity of everybody else. So it needs to be a nearby enough galaxy so that it's big enough on the sky. You can follow, say, the stars. Of course, the beautiful example is Sagittarius A star, where we have all the stars around our own, but that's only that one, right? But for these other galaxies, it's not so easy. But so for nearby galaxies, many of them, you have some sort of estimate of the mass of the black hole and the velocity dispersion of the galaxy, and they follow this kind of scaling law, okay? And so the next thing that you can do, but this you have for the local universe. So the next thing that you can do is I go out there, and now I can look at all the galaxies that I can find and measure their velocity dispersion. That's not so not as difficult as getting the mass of the black hole. I just need to take spectra of all of these galaxies and look at the lines and see the velocity dispersion. So I can count galaxies as a function of the velocity dispersion, and then I can use this to know how many, the mass in black holes, right? For each of these galaxies, I know the velocity dispersion. I go to here, I know the black hole that they have, or I think I know, and they count the black hole's mass in this way, okay? So in other words, I need some sort of distribution or velocity dispersion function, for example, it's called, which gives you the number density of galaxies as a function of their velocity dispersion, plus or coupled with this allows you to compute the number density of black holes in the universe, which is given by the number density of galaxies, and then associated to each of these galaxies one of these black holes, okay? So that's another route to do it, okay? So people have counted galaxies as a function of black hole. For example, for big redshift surveys, there's many estimates. And there are estimates of the M sigma relation, okay? And so you can do this, you plug it in, and you, for example, can compute the mass density of black holes by multiplying this and integrating, okay? So you count the galaxies, go to here, compute how many, this is another function, right? So the black hole mass function, and you get the rho in black holes, okay? That's another road, and the answer is the same as that one over there, okay? So, that's, yeah.
Just, you mentioned Sagittarius A star, so our galaxy has a 4 million solar mass black hole in it, but mass of the galaxy is 10 to the 11, or
yes.
12 solar masses, so it really doesn't follow that 1%.
No, it does, because, yeah, the 1%, I said you have to, that is a very rough one, because it mainly applies to elliptical galaxies, and then if you wanted to apply to spiral galaxies, you need to look at the bar. I mean, and it becomes more dicey. And that is a very, it does follow much better this M sigma relation. Okay, yeah.
So for further galaxies, do you need like the cosmological model to estimate the mass of the black hole?
No. This, okay, the assumption is that the galaxies that are further away, their black hole also follows this M sigma relation. If that is the case, then you just need to measure their velocity dispersion, and then use this to estimate the mass of the black hole.
Because you said like you need to measure the velocity dispersion near the black hole.
That would be in order to put this galaxy in this plot. So yeah, exactly. There are two steps to this problem, to this estimate. One of them would be to try to, what I cannot do is go out and get faraway galaxies, even not so far away. I can measure if you go to the literature and look at a paper tries to estimate, this has 100 galaxies, okay, something like 200, a small number, because also it's very time consuming to make this observation. You can only do it to nearby galaxies. So this scaling relation is based on a small number of local galaxies, roughly speaking, okay? What is much easier is to go out there and put a fiber on a lot of galaxies in half the sky and count galaxies as a function of their velocity dispersion, but I have no idea what black hole they have directly. I only know it through this, okay? So then you can ask the question, could it be that the faraway galaxies are different than the ones nearby? At some level, that's for sure correct due to the cosmological evolution, right? Probably that's correct. Now, if you look at the low redshift, most probably we're not particularly special. So the nearby galaxies and the galaxies a little bit further away at the low redshift are all more or less similar, and they all follow this, okay? So there might be some questions about the evolution in time of these and whether or not this affects the situation. But remember that in order for me to do this estimate, I am not trying to estimate the mass density of black holes at the high redshift. I only want to compute the black holes today. And then I will assume or ask the question, if they merge, what is the background? I only wanted to know today. Then I might not know when they merge, but that is only this small effect. So for me, it's not that I'm trying to estimate the mass of the black holes at high redshift or these raw black holes at high redshift. I'm trying to estimate it here because I am going to assume that they are the remnants of these mergers. Okay, I'm going to ask if they are the remnant of these mergers, what kind of background they can produce. And of course, if they didn't merge, they produce no background, and then I'm in trouble because I see a background. But I want to ask the question, if they merged, what background they produce. So I'm only trying to do this in the local universe. Even so, it's not obvious that this is completely foolproof. I think it's we would all believe that the nearby galaxies are not particularly different than at redshift 0 than some other neighborhood a little bit out there. But in detail, this would be true if you made a random selection of galaxies around us and a random selection of, or at least selected in the same way. But these are so difficult to observe that how something gets into the sample, why it was observed, and for example, a lot of these come from the Coma cluster, which is a nearby cluster of galaxies. So perhaps the galaxies in clusters are a little bit different than the typical galaxy that then I'm counting in this way. So there might be differences. I'm not saying, but I'm just telling you how the story goes, more or less. Remind myself. Wow. Okay, so what I was going to say, you can do this exercise, then you can, this exercise is better because if you count galaxies as a function of velocity dispersion and you know what mass of the black holes they have, you also know not just rho of the black holes, but you can give, if you know the mass, you can get this as well, this efficiency. So you can actually do the proper integral of this times that integrated over all the black holes and get also not just count the density of black holes, but also weight them by how much gravitational radiation they produce and get a sense of which mass of black holes, which galaxies are the ones that host the black holes that emit the most for, say, for the gravitational wave background. And when you do that exercise, so if you do this, and you will do it in the problem, you will get a density of black holes in the local universe, and then you can estimate, do this integral as a function, not just assuming everybody has the same mass like here, but there's a certain distribution of masses given by this, you integrate over that, you look at the integrand and you see which mass contributes the most, okay? And you will find that it's somewhere around 10 to the 9 solar masses. So black holes of around 10 to the 9 solar masses contribute the most to the gravitational wave background. Why? Because, of course, the heavier they are, the more energy they put out. So that is one part. But heavier black holes corresponds to galaxies with higher and higher velocity dispersions that are become rarer and rarer. So if you were to look at how many galaxies there are as a function of velocity dispersion, this function looks some power law with an exponential cutoff. Okay, astronomers fit it with something called the Schechter function. But so there is like a maximum velocity dispersion that after that, the number density drops very fast. And so if you were to ask the question, so that maximum velocity dispersion corresponds to a particular mass of the black hole. If you start going up much more than that, the number density of those galaxies that can host those very big black holes is dropping like a rock, okay? So those will not contribute to the background. On the contrary, if you start going to lower velocity dispersion functions, so here I'm just plotting phi of sigma versus sigma. If you start going to lower sigmas, there are more of these galaxies, but this slope is not very steep. And so you're killed by the fact that the black hole scales like sigma to the power 5, this scaling relation. So the black hole masses is much smaller as you move here, and they barely produce any gravitational waves because of this, right? Well, the m to the 5/3. Okay? So there is a mass that contributes the most, okay? And this is around 10 to the 9 solar masses. So if you were to look at, yeah, okay, you will do it. So let me not do it here in the problems. The other thing that, this logic that goes back to a paper by Sterl-Finney that I am citing in my notes here that I haven't given you, but I will give you. I forgot. So I spent a little bit of time telling you that because when you look at a given frequency, the emitted frequency was higher, and then the efficiency, the energy something a binary is putting out is bigger with the higher the frequency, and so it compensates partially for the redshift. So which makes it that the redshift dependence is not very important. There's another uncertainty, which is, did they merge? I see the black holes today. Did they merge? Did they merge twice, 3 times? Maybe I get a bigger background if I merge 100 times or something like that. Okay, so the more they merge, I get more mergers, more energy out. So at some level, this is true. But what kind of uncertainty does that bring? Okay, the fact that I don't know how many times they merge, if at all. Okay, so if they didn't merge, the answer is 0. But now, let's say they merge once, and I want to compare that with every black hole in the local universe merged twice or 3 times or 4 times or what have you, okay? Does this make a big difference or does it make a big difference? So in total, this thing depends like the mass to the 5/3, okay? M chirp to the 5/3. Why? There is the mass here and the m to the 2/3 from the V over C, okay? So let's say that I have a black hole and it merged once. So it comes from 2 half the size. Let's say there's also an eta. So the most of the gravitational waves come out if you do equal mass mergers. So let me discuss that case. But you can also generalize this if the mass is not equal mass, okay? And I'm going in this direction because once you plug in these numbers, which you will do in the exercise, you'll discover that with the canonical numbers, you don't even get to the background that was measured by the PTA. So clearly, everybody must be merging because, I mean, maybe the canonical estimate is a little bit off because there's something off here, something off there, it's astrophysics or whatever. But if things were not merging, you have no hope, right? So you want as many mergers as possible. So the redshift of the mergers, as I said, doesn't matter. What about did it merge just once or twice or 3 times? Now, first merger, they had half the mass. Second merger, 1/4 of the mass. Let's say they're all equal, and so on. They become smaller and smaller. The amount of energy goes to like mass to the 5/3, right? So the energy going in the previous mergers is going down and down and down because the masses are going down. And the whole series converges. You can integrate, you can sum infinite number of mergers or just one, and the answer differs by some sort of factor of 2, okay? So if I were to know the background of the row of gravitation of black holes around us, my estimate of the background of gravitational waves is not very uncertain, okay? I mean, it's very uncertain to the extent they either merge, there's nothing, right? But to the extent that most of them merge, whether they merge once or twice or by you can do it you can sum this series keeping some mass ratio, all of this, some simple formula. You do it, and you see there's not a big difference, right? Some factors of 2, okay? So however you do it, you plug in the numbers then with the canonical estimates, and you discover that the background that has been observed is kind of high, okay? So, so that, and you will do it in the exercise, so that kind of brings up the question, what's going on? Like, first, on the one hand, perhaps one should say the following thing, and I think I have to finish, no? Yeah, yeah. So on the one hand, the background that was observed is off from this estimate by some sort of factor of 4 or something like that. Pretty good, okay? So 0th approximation, this is what we are seeing, right? Because the spectrum also matches, the amplitude is what you might have expected if the, so that's the answer. Now, but in detail, it looks high, okay, by some sort of factor of 4 in the energy density. What's going on? Is there something off in these? Are we counting wrong the black holes in the local universe? Are we missing some? What mass could we be missing? Okay, those are questions that I don't know the answer, but that's where we stand. So at 0th order, the estimate works. There's multiple ways to get to the mass density of black holes through the Sultan argument or direct counting. Those agree more or less. The typical mass of the black holes, obviously then it will, given this M sigma relation, it will be given by this, wherever this cutoff of the number of galaxies as a function of velocity dispersion is, because that will mean you want to have the biggest black hole, but they're just not more, there's a maximum. And that sets the mass that you get, more or less, and then you do this estimate, and you're a little bit off. Okay, what's happening? We don't quite know. There's a little bit more information in the PTA data that I might discuss in the next lecture regarding, if they're very heavy, the number of black holes in a given frequency band that you are seeing in the sky are not so many, and those might lead to some observable effect. And we can say something about whether we are missing a population of very heavy black holes. I don't think that's what's happening, but I'll say something about that next time. Okay, so I'll stop there.